principal focus and twice the principal focus. So, object is between f and 2f. Again, for construction of the image, we will take two rays of light, one passing through the focal point and the other through the optical center, and as these rays of light are meeting here, you can say that the object is image formed is a real one, and you can clearly see that the size of the object is smaller than the size of the image. So, image formed will be magnified, real, and the position of the image is beyond 2f. Distance between the lens and the image is more than 2f. So, the image formed is beyond 2f, real, inverted and magnified. So, this slide shows you the example of the object being placed between f and 2f. Next situation is when object is exactly at the focal point of the lens. So, again we take these two rays, one passing through the parallel to the principal axis, passing through the focal point after refraction, and the other one passing through the optical center. And as you can clearly see, these rays of light are rendered parallel to each other. So, these rays of light will meet at infinity as the parallel rays of light meet at infinity. So, the image will be formed at infinity when the object is at f. As we previously discussed, when the object is at infinity, image is formed at f. When the object is at f, image is formed at infinity. So, this is the example of object being placed at focal point of the lens, and you can see that there is no image visible from this side. The last situation is when the object is at a distance less than the focal length of the lens. So, object is placed between O and F, C and F, the optical center and focal point of the lens. Again, for construction of the image, we will take two rays of light, one parallel to the principal axis passing through focal point and the other one passing through the optical center. And you can clearly see from this diagram that these rays of light are moving away from each other and they will never meet each other. But if we extend these rays of light on the other side, they will appear to be coming from a point. So, the image formed in this case is virtual, as the rays of light are not actually meeting, but they appear to be coming from a point. And you can see the size of the image is quite large in comparison to the size of the object, and image is formed behind the object. So, in this situation, the image is on the same side as the object and it is virtual, erect and magnified. So, from this whole discussion you can see that in all the situations the image formed by convex lens is a real one, except when the object is between optical center and focal point of the lens. In that case, the image formed will be virtual one. So, this gives you the example of uninverted virtual image formed by a convex lens when the object is very close at a distance less than the focal length of the lens. Next, we will discuss images formed by a concave lens. First situation is when the object is at infinity. When object is at infinity, the rays of light incident on the lens will be parallel. The ray of light directed towards the focal point of the lens will be rendered parallel to the principal axis. The ray of light passing through the optical center will pass undeflected, and these rays of light will appear to be coming from this point. So, the image formed is virtual and is formed at focal point of the lens and is formed on the same side on which the object is. So, the image is at f prime. So, this gives you the example of a concave lens and you can see the image of the far away object. When the object is within 2f, that is between f and 2f, in that case parallel ray of light will be refracted in such a way that it will appear to be coming from the focal point of the lens. Ray of light passing through the optical center will move undeflected and they will appear to be coming from a point. So, the image formed is again virtual, and as you can see the size of the image is smaller and on the same side. So, the image will be formed between f prime and 2f on the same side of the object, virtual, erect and diminished. Now, let us discuss about the magnification of a lens. Magnification or magnifying power of a lens is defined as the size of the ratio of size of the image to the size of the object. So, here we have got an object and a real image of that object formed by a convex lens. Height of the image is hi or size of the image is hi and size of the object is ho. So, the ratio of hi and ho is called magnification or linear magnifying power of a lens. So, hi over ho is denoted by small m, the magnifying power. Another way to define the magnifying power is that it is the ratio of distance of image from the optical center to the distance of object from the optical center. So, distance of image from the optical center is denoted by V, distance of object from optical center is denoted by U. So, the magnification is V divided by U. So, this gives you the magnification of the convex lens. Now, let us discuss about thin lens equation. If the object is placed at a distance, we will discuss for convex lens only. We have a convex lens and an object is placed at a distance d naught from this convex lens, and image of this convex lens, image of this object is formed at a distance di by this convex lens. Let h naught is the height of this object, hi is the height of the image. Now, from these two triangles, you can see that these two triangles are similar. So, corresponding ratio of the corresponding sides of these two triangles will be same, and from these ratios we find out a lens equation which is 1 over d naught plus 1 over di is equal to 1 over f, where d naught is the distance of the object, di is the distance of the image and f is the focal length of the lens. So, this equation is called lens equation and is quite important for calculating the distances of images or objects or focal lengths of the lens. If any two of these are known, third can be calculated. In that lens equation, we use sign conventions. So these are the sign conventions for the lenses. First of all, about focal lengths. The focal length is taken as positive for converging lens or convex lens, and focal length is taken as negative for diverging lens or concave lens. So for convex lens, f is positive, and for concave lens, f is negative. Then magnification. Magnification, m is positive for upright images, that is same orientation as the objects, or you can say uninverted images, erect images. For erect images, object and image is on the same side of the principal axis, so the magnification will be positive. M is negative for inverted images. In case of inverted images, the object and image, they are on the opposite sides of the principal axis. One is above the principal axis and the other one is below the principal axis. So in case of inverted images, the magnifying power is negative. Image distance. Image distance di is positive for real images, that is images on the opposite side of the lens from the object, that is direct image is on the other side, object is on the other side of the lens. So in that case, the distance of the image is taken as positive. Di is negative for virtual images. So distance of virtual images is negative. Virtual image is formed on the same side of the lens on which the object is present. So when the image formed is on the same side of the object, the distance of the image is taken as negative. Object distance, d naught. Object distance do is positive for real objects for which the light is diverging, and d naught is negative for virtual object towards which light converges. So these are some of the sign conventions which we use in case of the lens equation we discussed in previous slide. So in this lens equation, this d naught, di and f, the focal length of the lens, all these three are to be substituted with proper signs, taking care of the sign convention we have discussed just now. Defects in the image formation by the lens. The image formed by the lens is not an exact replica of the object. So this departure of the image formed by the lens from the object is called defect in image formation, or we call it aberration. These aberrations are of various types. First of all, we will discuss spherical aberration. This spherical aberration arises because of the spherical nature of the lens. The surfaces of the lens, this shows you an example of a convex lens, and you can see that the surfaces of the convex lens are spherical, and this convex lens is thicker at the center and thinner at the edges. Let us assume that a monochromatic light is incident on this lens. Monochromatic light means light of single frequency. So when this monochromatic light is incident on this lens, the rays of light which are closer to the principal axis of the lens, they travel larger distance through the body of the lens than the rays of light which are away from the principal axis of the lens. The rays of light which are closer to the principal axis are called paraxial rays. The rays of light which are away from the principal axis are called marginal rays. So these rays of light which are near to the principal axis, because they travel larger distance through the body of the lens or glass, they are deflected to the different extent than the rays of light which move from the edges of the lens. So they will be brought to focus at different points. They will meet at different points. So, instead of one object, one image being formed for one object, we will have different images formed. So, peripheral rays and axial rays having different focal points caused by the spherical shape of the lens or surfaces causes the image to appear hazy or blurred and slightly out of focus. So, this image which is formed at here will be slightly out of focus and will be blurred and will not be the exact replica, and as this aberration arises because of the spherical nature of the lens, this aberration is called spherical aberration. The other type of aberration is called chromatic aberration. Chromatic means colors. We know white light consists of 7 colors, and when this white light is incident on lens, the refractive index of this lens is dependent upon frequency of the light, which is called, this phenomena is called dispersion. Because of dependence of refractive index on the frequency of light, different colors of light will be brought to focus at different positions. So, blue will bend maximum and red will bend minimum. So, a white point on this side of the lens will appear to be colored on this side of the lens. We will get 7 points corresponding to each color. If you place a screen over here, you will get central red flanked by the 7 colored spots, and if you place your screen here, you will get central blue flanked by the 7 colors and the outermost being the red. So, as this aberration arises because of the dependence of refractive index on the frequency, we call this as chromatic aberration. So, blue light is refracted to the greatest extent, followed by green and red light, a phenomena commonly referred to as dispersion. A converging lens can be combined with a weaker diverging lens so that the chromatic aberration cancels. So, what we do? We use a combination of a convex lens and a concave lens, and this lens is called achromatic lens or achromat doublet. So, this achromatic lens reduces the chromatic aberration considerably. Now, let us discuss an example. An object of height 5 centimeter is placed at 15 centimeter from a convex lens of focal length 10 centimeter. Find the position and magnification of the image, and this we will do from a diagram. You can use lens equation for the same, for solving the same example, but we will solve this example by constructing the ray diagram. So, our object is placed at 15 centimeter from the lens having focal length 10 centimeter. So, this represents the 10 centimeter. Each small box in this diagram represents, in this graph paper represents 1 centimeter. So, the focal point of the lens is at 10 centimeter, object is placed at 15 centimeter, and height of this object is 5 centimeters. So, let us construct the image of this object. So, this will be the image, and from this diagram you can see what is the height of the image. Height of the image is 10 centimeters. So, height of the image is 10 centimeters, height of the object is 5 centimeters. Therefore, the magnifying power is equal to height of the image over height of the object, which is equal to 2. And this magnifying power of a lens is a simple number, unitless, because centimeter cancels with centimeter. So, magnifying power is a unitless, dimensionless quantity. Thank you very much.